national conferences, and he has more than 10 journal papers, publications, and several patents on his name. I welcome Dr. Suhas Moite, sir, for our FDP, and I request Dr. Suhas Moite, sir, to start this session. Hand over to Dr. Suhas Moite, sir.
Thank you for that introduction.
Yeah.
Only thing is there is a small correction. I don't
Yeah.
have any patents in my name. Shall we start? Shall I?
Yes, sir. Yes, sir. We can start. You can share your screen.
Yeah. Where do I get that? Because these three
sir,
dots.
Below, yeah. You can see the three dots. You can just
but
put the cursor over
it has got a different menu, like change layout and those things are there.
No, sir, not three dot. Besides three dot, present now is there. Present now.
Okay. Yeah.
Click on that present.
From
now.
present now you can present, sir.
Yeah. From present now, click on present now and say
Entire screen.
Entire screen. Yeah.
Is my screen visible?
Not yet, sir.
No, sir. No, sir.
Yeah, it will be.
I think, sir, you have not clicked the present now. Entire screen you click, and there is OK or something like that. Share or something like that. You can click
share.
that. Yeah.
Share is there.
Uh-huh.
Share your entire screen. Okay.
Yeah.
But share is not getting initialized.
You can click on that particular figure first of all, which entire screen is coming. Some figures are there. So you can click on that, then share will be activated.
Yeah.
Now it is in transition. Yeah, presentation is in transition. Correct.
Yes, sir.
Now it is visible.
Right.
It is visible.
Sir, full screen kara, sir.
Yeah.
Yes, sir. Now it is perfect. Sir.
So good morning all.
Good morning, sir.
I hope most of the participants have joined. So the last 2 days, in fact, I had been to some of the presentations in past 2 days, and it has been a feast to listen to eminent speakers with the state-of-the-art technology examples that they showcased. So I will be touching on to the basic aspects of MEMS because in my opinion, many of the participants are new to this particular field and they are from different backgrounds. So I have decided to, connect few dots from what they know, and then we will move on to what is new and to many of the participants. So mechatronics is something most of us are familiar with. So let us have a quick look at that, and then we will move to MEMS and nanotechnology, how the scaling takes place. The outline is going to be like we will take a bird's eye view, and then we'll see how the scale of the things changes from meso, micro, and nano, and then we will just take a quick look at the history behind these developments, which dates back to 70 or 80 years. Then the important thing that is fundamental to the development of MEMS is microelectronics, from where the MEMS has evolved. And then it is the IC fabrication technology which is actually at the generic form to the MEMS. MEMS initiated from there. So initially it depended heavily on IC fabrication technology and the processes and the materials used there. And later on, now there are several other materials, as you came to know 2 days back from Professor Anand Suresh, who said that polymers and glass and several other new materials are being used in MEMS. So now MEMS have grown quite a lot, and therefore materials and processing also has now, which was earlier dependent heavily on IC fabrication technologies and the processes and materials related to that. But new materials and new processes have come in a big way with the development in MEMS. Then the fabrication also has been basically generically, it comes from the IC fabrication. Then we'll see some of the aspects of design and analysis of MEMS and packaging. And then we will take an overview of applications. And one application I would like to deal with in a little more detail, that is MEMS gyroscope or angular rate sensor. And then we'll see what are detail, that is MEMS gyroscope or angular rate sensor. And then we'll see what are the challenges and possibilities for the new researchers in the field of MEMS. So mechatronics, which we are all familiar with, all the mechanical, electrical, electronics, instrumentation, control engineering, computer, even IT people are also familiar with these, because these days we talk about Internet of Things or industrial Internet of Things, Industry 4.0, where there is a extensive use of sensors, collection of data and data analytics and interpretation. These things are being talked about in a big way these days. And you think of a thing and we talk about mounting sensors onto that, and several new areas are emerging with the integration of different technologies. So mechatronics has begun several decades back, and it has grown into the need of several sensors. And micro electromechanical systems is a miniaturization sort of, you can say, of that particular got sensors, actuators, and controllers which control these devices. But essentially what goes into these is sensors play a very vital role, and need and development of various kinds of sensors has gone in a big way, and the development is taking place in the area of MEMS, where these devices are fabricated on a silicon wafer alongside the electronics. And the integration, unlike in mechatronics, you can see the different devices separately. In MEMS, the integration is very, very strong and very close. So it is difficult to, differentiate. The electronics and the mechanical devices are sitting pretty close on a substrate. And that is the beauty of MEMS that you can see here. This is apparently a integrated circuit chip, but it has got moving mechanical structures sitting inside it. And these structures, when acted upon by certain physical signals such as pressure, acceleration, rotation rate, or, and things like that, they undergo deformations, which results into transduction. Various types of transduction principles are used in these devices, such as capacitive transduction, piezoelectric, piezoresistive, and so on and so forth, where the electrical signal is created, and that tiny electrical signal, where the change in the capacitance could be of the order of pico, femto, or autofarad, which is extremely small, but immediately the electronics is sitting next to it, and therefore these devices are in some sense protected from the noise in the environment, because there is not a big gap between the sensor where the tiny signal is produced and the electronic circuits which carry out the immediate signal processing, such as the amplification, the filtering, and similar processes on the signal processing circuits that are built in the vicinity with various kinds of operational amplifiers and devices. Then the sample and hold and all those circuits, which will be sitting very pretty close to the transducer, and therefore there is a little loss of signal, and there is little loss of scope for the noise to play a role there. Although the signal that is available is pretty small, but there is a amplification that takes place in the immediate vicinity alongside the electronics. So in MEMS, there is a strong integration of mechanical and electronic devices, and you can see several miniature devices are fabricated on. Those who are familiar, electronics people are familiar with CMOS circuits. They know that there are several capacitances that come into picture, and there are deliberately manufactured parallel plate capacitance or comb fingers that can be built using this silicon fabrication technology. Even inductors are possibly can be created. A simple cantilever beam or diaphragms can be fabricated on this silicon substrate, and various transducers can be realized. So, and in the end, you will have this particular packaged integrated circuit chip, which can sit onto a small board, which is on the tip of a finger. And you have energy harvester, for example. In this picture you can see an energy harvester. Here you can see another device that is sitting inside the chip, and then you can see a gyro or an accelerometer or a pressure transducer that is subjected to that is sitting in a small packaged device, which is totally protected, and it can work into any kind of environment. And the next thing after mechatronics, we discuss MEMS. Just a small look at the technology, and then the nano electromechanical systems are also being talked about, and we hear quite a lot these days. So it's the scale of the things that is getting changed by almost 3 orders of magnitude, from meso, micro, and nano. So there is a 3-order magnitude shift in the uh, scale that is being talked about, and there is a possibility that was, envisaged by Richard Feynman and Gordon Moore and likes 50 years back, 60 years back, and the technology is being realized in modern times. And we talk about nanoparticles of various sizes. There are various kinds of surfaces and chemistry that goes into a variety of shapes that can be created, and different materials have emerged these days, such as graphene, carbon nanotube, and several types of polymers and metallic particles and hydrogels, and several applications too have come up with the advent of these. And especially the field of medicine has undergone tremendous change, and it is going to offer several things in the days to come with the various developments that are taking place. And this is how you can manipulate at various scales. So nanotechnology is the era where 1 to 100 nanometer, that means this is the scale in which things are manipulated in nanotechnology. Whereas in micro electromechanical systems, it is from fractional micron to several hundred micrometers is the range in which MEMS comes into picture. And whereas the mesoscale devices are in millimeter to meter scale, which we are all familiar with. So thus, I hope you have got that this is a millimeter, micrometer, and nanometer scales of the things that they function. And with these scales, in fact, you have several other significances that are attached to these changing scales of milli, micro, and nanoscale materials, because you have the response times scaling in the same order as that of milliseconds, microseconds, and nanoseconds, or the operating frequencies that we can use are in meso kilohertz, then megahertz and gigahertz. So that is how things are also alongside scaling. When the physical dimensions undergo change, the time scales also undergo change. That is something you have to keep in mind, because the device response time also reduces or shrinks considerably by orders of magnitude. We used to have kilobyte memories, and megabyte, gigabyte, and terabyte memories are possible because of the shrinking length scales of these devices. So now let us move on to the MEMS and MEMS technology. So for past 2 days, you know that MEMS is micro and electromechanical systems, which are integrated systems. The functionalities are integrated. The components are exchanging signals across the boundaries of the domains: mechanical domain, electrical domain, fluid and thermal domain. 2 days back, you saw the thermoelectric tweezer. An example was given by Professor Anand Suresh. So various domains. In mechanical domain, you have structural, thermal, and fluids interacting with electrical uh, quantities such as capacitance or changes in capacitance, inductors, or resistance changes, which in turn are converted into some kind of sensors, and then electronics processes those signals for the purpose of analysis and then further actions and applications, which is driven by these various levels, from physical to electromechanical, then electronic, and then computational part if needed, that can come into picture, and data analytics. And that is how at various scales the applications are growing with the advent of this technology. The size, it takes a while for a new person to come to terms with the size of the devices that we are talking about. So these are some of the marvelous creations. Friends, mind well that you are all currently using these MEMS devices, and these devices are very much sitting in your mobile phone, which you are carrying in your pockets. I don't know whether you have ever wondered how small is the microphone and the speaker, micro speaker rather, that is there in your mobile phone, and what is the technology that goes into manufacturing of those microphones. So those are essentially MEMS microphones, which are produced on large scale with batch fabrication technology using silicon micro machining. The speakers too are being manufactured with this technology. Then you have what is known as a rotation rate sensor. As you tilt your mobile phone or turn your mobile phone, the screen flips from a portrait to landscape, and that is basically a sensor which senses this rotation or movement and responds to the change that is experienced by the device. So that's why we call it a smartphone or smart device, because it responds to the environmental change. It can show you your blood pressure, it can show you your stress level, and I mean, mobile phone is one thing, but there are several other applications that are emerging with the mobile phone, such as it can monitor your blood pressure. It's all possible because of the sensors that are being fabricated at a miniature level, at a uh, affordable level, at a large scale, with the same technology that goes into the fabrication of electronic devices. So this is something that has to be kept in mind or borne in mind by mechanical engineers, that conventionally we use various mechanical manufacturing processes. However, MEMS devices essentially make use of additive and subtractive manufacturing and the processes that go into manufacturing of electronic circuits. So IC fabrication technology or the processes that are being used by a MEMS fraternity. So this is another important thing. Not only that, the material in mechanical engineering, the conventional materials are various types of metals and metal alloys, steels, iron and aluminum, copper, and so on and so forth. However, they are not amenable to the IC fabrication technology. So IC fabrication technology essentially with germanium or silicon wafers, it has emerged and it has developed and grown and advanced. And therefore, there was a need to, when mechanical engineering tried to enter into this, these were the constraints and limitations, and therefore mechanical engineers, they adopted to this silicon as the mechanical material. Silicon was never talked about mechanical materials. However, silicon is being used as mechanical engineers, and that is how the emergence of MEMS has occurred. Microelectromechanical systems have got sensors, miniature sensors, microactuators, microstructures, means devices, and microelectronics. So it's an integration, a very strong integration of sensors, actuators, electronics, and microstructures. Now, the sensors can be as small as possible, and functionally they do not have any issue. Whereas actuators can be micro or meso or large scale, because when you want to operate in physical world something huge, then you have to have big actuators. Miniature actuators are also possible, especially they are suitable in medical applications. However, when you are wanting to do something in the meso world, then obviously the actuator part is going to be big. So this particular another important aspect has to be borne in mind. So you can have sensors as small as possible, but then it helps in several ways. You can have arrays of sensors that can be deployed to collect several data of different kind, and a variety of sensors also can be deployed in a certain application to acquire a variety of different signals such as temperature, pressure, flow, and light intensity, acceleration, rotations, etc., etc. Several parameters can be sensed by a variety of sensors, and you can have array of similar or a variety of sensors deployed in a certain application. And essentially what is needed is sensor, and the electronics needs to be a miniature. Earlier what happened is electronics scaled down several orders of magnitude since the advent of first transistor, which was of the size of few millimeters, and later on it became of micron, and these days it is at the nano scale. However, the mechanical devices did not scale down that much, but MEMS technology did that particular thing by integrating itself with the IC fabrication technology. So an important factor in the progress of miniaturization technologies is MEMS and mechatronics. Micromechatronics, it can be called as micromechatronics. MEMS consists of integral micromechanical and microelectronic elements fabricated by established semiconductor processing technology. This is another important. Various types of sensors such as pressure sensors, acceleration sensors, gyroscopes, microphones, and so on and so forth. Actuators of a different kind, linear and rotary actuators, miniature actuators we are talking here, valves. There are drug delivery systems where there are miniature pumps that can be mounted onto human body, or the devices can be worn on the wrist or any part of the body. So wearable devices have come in where the drug delivery system is there, where there is a tiny pump, a miniature pump, and there is a tank that can hold a microgram of medicines. So then there are tweezers to manipulate things at micro level. The one of thermoelectric tweezer that you saw the other day. There are varieties of motors, gears, gear trains, turbines, nozzles, and pumps that are fabricated as actuators using MEMS technology. It's a critical technology in the fields such as aerospace, has got huge applications, automotive applications, biomedical, and communication industries. Commercial applications of the MEMS include microfluidics, and then manipulators for implantable drug dispensers, navigation gyros for aerospace use, and magnetic and optical storage and switching devices, which are very popular, and radio frequency MEMS also you might have heard about, and displays for the projectors and information technology. The advent of MEMS goes back, or the nanotechnology that we are talking today, and you must have heard the famous talk given by Richard Feynman, where he proposed the possibility of ultra miniaturization or the size reduction by 3 orders or more than 3 orders of magnitude in mechanical systems, as well as miniaturization of computers to the levels involving the manipulation of atoms. You might have heard about single electron device also. So that means a switch can, how small a switch can be, it can go down to a level of presence or absence of an electron. So such is the possibility that one can think about when things get miniaturizing, the switch can be represented by a presence and absence of electron. Although we have now very nanoscaled transistors available these days with 10 nanometer technology, while these possibilities were envisaged, envisaged by these visionaries around 70 years back. While these ideas were undoubtedly prophetic in those days, the technique envisaged of three-dimensional machines iteratively making ever smaller and smaller versions, one machine making another machine smaller than itself, and so on and so forth. That is how the idea put forth by Richard Feynman, and it was unlikely ever to be practical, a point acknowledged by Feynman himself after revising the concept in 1983. Nano-electromechanical systems, or NEMS, is the next logical miniaturization step from MEMS and is used to describe devices integrating electrical and mechanical functionality on nanoscale. Often employing the 2010 Nobel Physics Prize-winning material graphene. You must have heard about this material graphene, which is a landmark development in the field of nanotechnology. And this material is finding a lot of applications. It has got properties that are extremely beneficial. And this is atomic force microscopy is also developed here. And it has got several applications because you can manipulate at that scale. Currently, the most significant technology for the fabrication of three-dimensional MEMS microstructures are bulk micromachining and surface micromachining. Besides that, there are other processes such as LIGA and EDM and substrate bonding, etc. NEMS systems rely on two basic principles of fabrication: photo and electron beam lithography. Photolithography or electron beam lithography, and molecular self-assembly, because nanotechnology is a level where you manipulate molecules, and molecules have got dimensions of fractional nanometers or in angstroms, and with the these atomic force microscopy you can manipulate these particles at nanoscales. So this is a new development that is expected to, and it is taking place in a big way. Now let us have a fresh look at the scale of the things that is occurring in the nature and that are developed by humans. This scale starts at 1 centimeter and ends at 1 angstrom. From centimeter to angstrom are the two extremes of this particular scale. At the centimeter scale or millimeter scale, what you find is the ants, which are approximately 5 millimeters, and then dust mites, which are 200 micrometer, which is 0.2 millimeter, fractional millimeter, followed by fly ash, which is 10 to 20 micrometer. Human hair range from 60 to 120 or 100 to 200 also. If thick hair are there, you can have the human hair thickness is 200 micrometer. We need to know the scale of few things so that we can relate. Otherwise, numbers are do not make sense unless we relate them to something physical. Red blood cells are 7 to 8 micrometer in size, and you have 10 nanometer ATP molecules which can be synthesized and which are available in nature. So those can be even synthesized manually in laboratories. Then you have DNAs and atoms which have got these molecules, and this is the atoms of silicon spacing tens of nanometer. See, there is a huge gap between these atoms. I will take a pause here. You have to watch this particular picture where we are seeing atoms, and the atoms have got a huge void in between them. Atoms of silicons are being seen, and there are tenths of nanometer. That means the size of atom is a fractional nanometer, but the gap between the atoms is several times their own size in solids, in silicon. Richard Feynman has said that there is plenty of room at the bottom. This is the room that he was referring to. That means the atoms, or you all of you probably must be remembering Rutherford's experiment with alpha particles, I suppose, where he found that when he sent the high velocity alpha particles through the foil, gold foil, several particles, large number of particles, they went straight. What it meant was that there was a void that allowed the particles, which are helium atom particles, passing through gold foil, a thin gold foil, and most of the particles were found to go straight. What it means is that there was a void. So that means something that is not visible to our eyes doesn't mean that it doesn't exist. There exists a huge gap in solids, and that particular gap between the, I hope you are getting. Hello?
Yes, sir, perfectly. Yeah.
Yeah. See, I'm trying to, make you think on your own about what is there in between atoms. I mean, when we say that there are atoms, the structure of atom also we have all studied. There is a nucleus and there are orbits. But what is there in between the nucleus and the orbits? There is a gap. There is a gap there, right? So that means there is void actually, even within an atom. Between atoms, there is a huge void. Between molecules, there is a huge void. And among molecules also, for example, if you take air molecules, mechanical engineers are aware of one term called as, what is that? Mean free path of gas molecules or air molecules. It is 70 nanometers. What is the meaning of mean free path? It is in kinetic theory of gases, the molecules of gas are continuously in random motion, and they collide with one another, and this average distance of collision is 70 nanometers. Average distance of collision is 70 nanometers. Now think about an oxygen molecule. The radius of oxygen molecule may be a fractional nanometer, or nitrogen, a fractional nanometer, because it is few angstroms, 2, 3, 4 angstroms, which is fractional nanometer. And these molecules are there present in the air that is around us, within us, where we are ourselves immersed in this particular air. But these molecules are separated at that scale. They are separated on an average a distance of almost 100 times their own size. For example, if 7 angstrom is the radius, let us assume that 7 angstrom is the radius of a particular gas molecule, which is 0.7 nanometer, and the average distance between the collision of two molecules is 70 nanometers, which is 100 times. That means there is a gap of 100 molecules in between two molecules on an average. in a gas, right? So there is plenty of room at the bottom. And even if you take the case of solid, as I told you, the example of Rutherford's experiment, where he impinged these helium nuclei over a gold foil, and several alpha particles went straight, meaning that they found a void there. So this particular aspect has to be kept in mind, that we as a human, we have certain limitations of vision, and but the thought doesn't have a limitation, and that is the difference between us and those visionaries that I referred to. Richard Feynman had this particular vision that when the structure of an atom molecule was conceived, the concept was evolved, then they thought about the scale and the size of these things, and then the size that gave rise to the thought process of what is the gap between these two, and can we manipulate those devices. Even those things were not possible at physical level in those times, but at the mental level they could envisage this, at the mental level they could imagine this. So that is how you can, there is a thought process that can start even if you give a small attention to this particular fact of what is the gap between the atoms. Now we have these man-made things which are head of a pin, and then micro electromechanical devices that are fabricated on silicon wafer, which are tiny devices like this. Then you have red blood cells, which are here for comparison with these gears. These blood cells are of this size, and the devices that can be fabricated. So the possibilities, you have to first of all come to terms with that these possibilities are there, and that is what the technology, MEMS and nanotechnology, that is being talked about. The fabrication of a combined nanoscale building blocks to make a useful device, for example, photosynthesis reaction center with the integral semiconductor storage. So, this is how tiny building blocks can be. The way a transistor is a basic building block, similar to that, a transistor is a basic building block. Similarly, molecules are the basic building blocks in nanotechnology. Remember, a transistor is a basic building block in microelectronics. On the similar lines, you have molecules as the basic building blocks in nanotechnology. So that once that fact is understood and digested, then it is possible to imagine further. These are the carbon nanotubes. And then you have these atoms of iron. 48 atoms of iron are being arranged in the form of a coral here on the copper surface, positioned one at a time. An STP tip, a scanning tunneling microscope is used. Scanning tunneling microscope is used, and its tip has carried these iron atoms, and they have been arranged in this. So that means nanotechnology is about manipulating atoms and molecules. This technology was envisaged 70 years back. It has become practicable today, and it is opening new possibilities and being referred to as nanoscience, nanotechnology, nanoengineering, so on and so forth. But it is all about what we do at mesoscale, the kinds of assemblies that we do at mesoscales, the kind of assemblies that we do at micro level, and the kind of manipulations that we do at nano level. This is the scale of the things is changing. Most ideas remain the same. So thus this is a historical background that we touched upon, and these visionaries, we must remember them, that there is a plenty of room at the bottom is what he said. It was a talk given in American Physical Society in Caltech in December 29, 1959. Feynman described a process by which the ability to manipulate individual atoms and molecules might be developed using one set of precise tools to build and operate another proportionally smaller set, and so down to the needed scale. So this was a thought that was put forth way back. Another visionary is the number of transistors, as most of the electronics people are very familiar with this. On a chip will double every 2 years. In fact, the law got modified, and it took 18 months for the doubling of and the process is on. And this was said in 1965, and now it has been more than 50 years. The Intel founders' words Intel has kept the pace of over 40 years or 50 years rather, providing more functions on a chip